1.5 million kilometers from the swirling blue and white marble of Earth, the silence of the vacuum is absolute. In this airless theatre, where the heat of the sun is a constant punishing pressure, a monument to human curiosity hangs suspended at the second Lagrange point. Here, the gravitational pull of the Earth and the sun find a rare and delicate equilibrium, creating a stable anchorage in the velvet dark. This is the home of the James Webb Space Telescope, a sentinel standing guard at the threshold of the deep. It is a construction of gold, silicon and beryllium, shielded from the thermal fury of our home star by 5 gossamer layers of silvered plastic, each no thicker than a human hair. This sun shield, a shimmering kite the size of a tennis court, creates a shadow of profound cold. On the sunward side, temperatures climb to nearly 85 degrees Celsius, while on the shadowed side, the instruments dwell in a frozen realm of 233 degrees below zero. In this frigid sanctuary, the primary mirror glows with the luster of pure gold. It is a honeycomb of 18 hexagonal plates, together forming a single aperture 6.5 meters across. This is a singular eye, designed to catch the faintest whispers of infrared light that have travelled across the cosmos for billions of years. To look into this mirror is to look into a machine that can see the birth of the first stars, the ignition of the very first galaxies that flickered into existence when the universe was less than 5% of its current age. For years, this golden eye has stared into the deepest reaches of time, mapping the expansion of the void and the formation of the cosmic web. But today, the great machine begins a silent, agonizingly precise rotation. There is no sound of gears grinding, no hiss of hydraulics. Instead, internal reaction wheels spin with measured intensity, generating the subtle torque required to pivot the entire 10-ton structure. The golden eye swings away from the edge of the observable universe, turning its gaze toward a target that is, by comparison, on our very doorstep. It looks toward the southern constellation of Centaurus, specifically toward a point of light that has guided navigators across the southern oceans for millennia. The target is Alpha Centauri. At a distance of 4.3 light-years, it is the closest stellar system to our own Sun. To the naked eye from Earth, it appears as a single brilliant spark, the third brightest in the night sky. But through the infrared vision of this golden sentinel, the truth of the system begins to resolve. It is not one star, but a complex triple-star ballet. 2 great suns, Alpha Centauri Alpha and Alpha Centauri Beta, are locked in a tight gravitational embrace, while a third, much smaller companion, Proxima Centauri, drifts in the far distance, a lonely ember at the edge of the system. The light that the telescope now gathers left those stars only 4 years and 4 months ago. This is a staggering contrast to the light from the deep field, which may have spent 13 billion years traversing the expanding void. Yet this proximity brings its own challenges. The brightness of these neighbouring suns is a torrential flood of photons that threatens to overwhelm the sensitive sensors. The telescope must use its coronagraph, a series of internal masks to physically block the light of the stars themselves. This allows the scientists on Earth to see the faint warm signatures of the worlds that might be hiding in the shadows, planets that have remained invisible to every other telescope in human history. The precision required for this manoeuvre is almost beyond comprehension. As the telescope settles on its target, its mirrors are aligned to within a fraction of the wavelength of light. Actuators behind each hexagonal segment move in increments of nanometers, thinner than a strand of deoxyribonucleic acid, ensuring that the 18 individual reflections merge into one perfect image. The telescope is now a steady, unblinking witness to the mechanics of our nearest neighbours. It is no longer looking at the ghosts of the ancient past, but at the living, burning reality of the stars that share our corner of the Milky Way. As the data begins to stream back to Earth, traversing the 1.5 million kilometres in a matter of seconds, the true nature of the Alpha Centauri system begins to emerge. We are no longer looking at a distant point of light, but at a landscape of fire and gravity. The transition is complete. The golden eye has finished its long look into the dawn of time and has turned its attention to the neighbours we have dreamed of visiting for generations. In the absolute quiet of the second Lagrange point, The machine waits, its sensors drinking in the infrared glow of a system that may hold the answer to our most fundamental question: are we truly alone in the dark? The vastness of the gap between our Sun and Alpha Centauri is difficult to grasp, even for those who spend their lives mapping it. If the Sun were the size of a grain of sand, the Earth would be an invisible speck an inch away, and Alpha Centauri would be another grain of sand located 10 miles distant. Between those two grains lies nothing but the interstellar medium, a sparse sea of dilute plasma, cosmic rays, and the occasional atom of hydrogen. To cross this distance is to cross a desert of such scale that the human mind naturally recoils. Yet, the James Webb Space Telescope bridges this gap with its gaze, turning the 4-light-year void into a laboratory. The precision of the machinery is the only thing that allows us to bridge this distance, a testament to a species that remains tethered to a single planet but has learned to see across the stars. Leaving the gravitational anchor of the second Lagrange point, the journey into the deep begins with a slow, agonizing retreat from the warmth of the inner solar system. The Sun, once a dominant furnace that filled the sky with blinding white light and governed the motion of every planet, begins to lose its authority. As the distance grows, the familiar features of our home system dissolve into the dark. The Earth and its moon become a single, flickering point of light, eventually vanishing altogether. The gas giants Jupiter and Saturn, which loom so large in our local imagination, are reduced to wandering specks before they too are swallowed by the encroaching blackness. The Sun itself, the source of all life and energy we have ever known, shrinks steadily, its golden corona thinning until it is indistinguishable from the other stars that populate the Orion arm of the Milky Way. The transition from the solar system to the interstellar void is marked by the crossing of the heliopause, the invisible boundary where the solar wind, a constant stream of charged particles from our Sun, finally falters against the pressure of the galaxy. Beyond this threshold lies the interstellar medium, a realm that is often described as empty, yet is teeming with the ghosts of dead stars and the raw materials of those yet to be born. This is not a void of absolute nothingness, but a sea of dilute plasma, a thin broth of hydrogen and helium atoms that have drifted for eons. It is a place of profound cold and silence, where the density of matter is so low that a single cubic centimetre of space might contain only 1 or 2 lonely atoms. Through this sparse medium, cosmic rays streak like invisible bullets. These are high-energy protons and atomic nuclei, accelerated to nearly the speed of light by the violent deaths of distant supernovae or the churning maws of black holes at the galactic centre. They are the true inhabitants of the void, a constant silent rain of radiation that permeates the darkness. The magnetic fields of the galaxy twist and coil through this space, guiding the flow of plasma in a slow, celestial current that spans thousands of light years. To traverse this medium is to move through a textured, energetic landscape that is invisible to the human eye, but felt by every instrument and every atom of a departing craft. The scale of this crossing is defined by the ultimate speed limit of the universe. Light, the fastest messenger in existence, travels at nearly 300,000 kilometers per second. At such a velocity, a photon could circle the Earth 7 times in a single heartbeat. Yet, even at this staggering pace, the journey to Alpha Centauri is a marathon that spans years. To bridge the gap of 4.3 light-years, a beam of light must travel for more than 1,500 days through the dark. This is a distance of roughly 40 trillion kilometers, a number so vast that it renders traditional units of measurement meaningless. It is a gulf that separates not just 2 stars, but 2 distinct islands of existence. As the journey progresses, the Sun continues to recede, eventually becoming just another spark in the tapestry of the Milky Way. It loses its yellow hue and settles into the cold, blue-white brilliance of a distant star. From this vantage point, the solar system is no longer a place of bustling activity and complex orbits, but a silent, frozen memory. We are now in the true deep, the local galactic neighbourhood where the stars are separated by light-years of silence. The Orion Arm, a sprawling spiral of gas and dust, stretches out in every direction, containing hundreds of billions of suns, each an island in this vast, dark ocean. In this state of profound isolation, the destination begins to emerge from the background of the southern sky. Alpha Centauri, which appeared as a single point of light from the perspective of Earth, begins to reveal its true complex nature. The light we see from it now is 4 years old, a delayed postcard from a neighbour that is both tantalisingly close and impossibly distant. The void between us is a testament to the lonely reality of our corner of the galaxy. We are drifting through a neighbourhood where the nearest house is 40 trillion kilometres away, and the only bridge across that distance is the light that carries the secrets of its origin. The silence here is heavy, a weight that emphasises the fragility of any craft or consciousness that dares to cross it. There is no air to carry sound, no atmosphere to scatter light. There is only the sharp, needle-like brilliance of distant suns and the crushing vastness of the space between them. The journey across the 4.3 light-year void is a reminder that we live in a universe of islands, where the darkness is the rule and the light is the rare, precious exception. As we approach the Alpha Centauri system, the 3 suns that compose it begin to exert their gravitational influence, pulling us out of the neutral territory of the interstellar medium and into a new chaotic laboratory of gravity and fire. The void is behind us, but the challenges of this new system are only just beginning to manifest in the senses of the approaching observer. The quest to understand our place among the stars did not begin with golden mirrors in the vacuum, but with brass tubes and ink-stained ledgers on the windswept coasts of the 19th century. In the early 1830s, the celestial sphere was still, for many, a rigid canopy, a finite boundary where the stars were fixed like diamonds on a velvet curtain. But for the astronomers of the age, a quiet obsession was taking hold, the search for stellar parallax. They knew that if the Earth truly orbited the Sun, the stars should appear to shift ever so slightly against the background of more distant objects, as our planet moved from one side of its orbit to the other. To find this shift was to prove the motion of our world and, more importantly, to measure the true scale of the heavens. Thomas Henderson, a Scotsman of meticulous habit and quiet resolve, arrived at the Cape of Good Hope in 1832 to take up the post of His Majesty's astronomer. The observatory sat on a lonely scrub-covered hill, buffeted by the salt-laden winds of the South Atlantic. His primary tool was the mural circle, a massive vertically mounted ring of brass and iron, 6 feet in diameter, fixed to a solid stone wall and calibrated with microscopic precision. Night after night, Henderson sat in the damp cold of the southern winter, watching as the brilliant spark of Alpha Centauri crossed the meridian. He used the transit instrument to mark the exact moment of its passage, his eye pressed to a telescope as he tracked the star's journey across a fine web of spider silk stretched within the eyepiece. The silk, harvested from local Cape spiders, provided the thinnest possible lines against which to measure the passage of a sun. Alpha Centauri was a prime candidate for this study. It was one of the brightest stars in the sky and showed a significant proper motion, a steady drifting across the sky over decades, which suggested it was closer to Earth than its peers. Henderson recorded hundreds of observations, measuring the vertical angle of the star with a precision that strained the limits of Victorian technology. He was looking for a deviation so small it was equivalent to measuring the width of a human hair from several kilometres away. Every vibration of the wind, every expansion of the metal from the heat of the day, and every error in the clockwork had to be accounted for and stripped away. When he finally sat down to calculate the results, the data revealed a staggering truth. Alpha Centauri was not just distant. It was millions of times further away than the Sun. While Henderson laboured in the southern hemisphere, Friedrich Bessel, a titan of German mathematics and astronomy, was conducting a parallel search from the Königsberg Observatory in Prussia. Bessel chose a different target, a dim, fast-moving star known as 61 Cygni. Bessel possessed a superior instrument called a heliometer, a telescope with a lens split into 2 halves that could be slid past one another to measure the angular distance between stars with unprecedented accuracy. In 1838, Bessel published his findings first, claiming the glory of being the first human to reliably measure the distance to a star. He calculated that 61 Cygni was some 10 light-years away, a distance that shattered the traditional concept of a compact cosmos. Henderson, hearing of Bessel's success, quickly published his own findings on Alpha Centauri in 1839. His calculations showed that our nearest neighbour was even closer than Bessel's star, yet still situated at a distance that defied easy comprehension. The realization sent a shockwave through the scientific community. The universe had suddenly and violently expanded in the human mind. The small universe of the ancients, where the stars were just beyond the planets, was dead. In its place stood a cold, terrifyingly vast abyss. The measurement of Alpha Centauri's parallax was the moment humanity first truly grasped its own loneliness. Henderson's data proved that the gap between our sun and the next was not a mere skip across a pond, but a voyage across a silent ocean of nothingness. The stars were no longer just lights. They were independent suns, separated by gulfs so wide that light itself took years to cross them. This was the birth of the modern interstellar scale, a realization that we were adrift in a galaxy of proportions that defied the grasp of the human mind. The mural circle and the transit instrument, for all their primitive elegance, had cracked the shell of the sky and revealed the true depth of the dark. This intellectual revolution transformed the stars from mythological symbols into physical destinations. The work of Henderson and Bessel turned the sky into a map of three-dimensional space, where every point of light occupied a specific lonely coordinate in the void. For Henderson, the Cape of Good Hope was the perfect vantage point to witness this expansion. As he looked at Alpha Centauri through his brass telescope, he was no longer seeing a light in the sky of Earth. He was looking at a gargantuan twin of our own sun, burning in the depths of a distance that would take 40 trillion kilometers to traverse. The era of the three-dimensional universe had begun, and the dream of one day crossing that gulf was born in the scratch of his quill on parchment, even as the stars themselves remained silent and out of reach. The two primary suns of the Alpha Centauri system stand as the central pillars of a celestial architecture far more complex than our own. Alpha Centauri. Alpha, the larger of the pair, is a yellow dwarf star that serves as a near-perfect analogue to our own Sun, yet it possesses a more formidable physical presence. It is approximately 25% more massive and significantly more luminous than the star that governs our solar system. Its surface is a churning sea of plasma, where convection currents rise and fall in a rhythmic golden pulse. From its outer atmosphere, a constant stream of charged particles, a stellar wind, rushes into the void, carving out a bubble of influence that mirrors our own heliosphere. This star is a spectroscopic twin to our Sun, but it is an older, more established sibling, burning with a steady, pale brilliance that has endured for billions of years. Orbiting this yellow giant is Alpha Centauri Beta, a star of a different character and hue. Beta is a slightly smaller, cooler star, classified as an orange dwarf. Its light is deeper and more saturated, casting a warm amber glow across the system. While it possesses about 90% of the mass of our Sun, its smaller size and lower surface temperature mean it radiates less energy. Yet, it is far from a dim companion. Together, these two suns dominate the local neighbourhood, their combined gravitational influence creating a massive double well in the fabric of space-time. They do not sit still, nor do they follow the simple circular paths we find in our own planetary arrangement. Instead, they are locked in a permanent spiralling embrace, a dance of two suns that has continued since the system first coalesced from a cloud of interstellar gas. This orbital dance is defined by a 50-year cycle of dramatic approach and retreat. The two stars follow highly elliptical paths around a common centre of mass, a point in the empty dark known as the barycenter. At their closest point, known as periastron, the distance between Alpha Centauri Alpha and Beta shrinks to a mere 11 astronomical units. This is a distance comparable to the gap between our Sun and the ringed planet Saturn. During this phase of the orbit, the gravitational tides between the two stars reach their peak, and any planet caught in the middle would see two distinct brilliant suns in its sky, their combined heat and light creating a season of intense radiation. As the decades pass, the stars begin their long, slow swing away from one another, eventually reaching a maximum separation of 35 astronomical units. At this distant point, known as a pastron, They are further apart than our Sun is from the frozen blue world of Neptune. Even at this extreme distance, the orange glow of Beta would still appear as a source of significant heat and light to any world orbiting Alpha, a second sun that never truly sets, but instead lingers as a bright, piercing ember in the night sky. This constant shifting of distance, from the proximity of Saturn to the isolation of Neptune, ensures that the gravitational environment of the system is never truly at rest. It is a rhythmic, grinding clockwork that dictates the stability and the very survival of any smaller bodies that might attempt to form within the system. The chemistry of these two suns reveals a history of cosmic abundance. When astronomers analyze the light from Alpha and Beta, they find a high concentration of what they call metallicity, the presence of elements heavier than hydrogen and helium. In this regard, the Alpha Centauri system is far wealthier than our own. It contains a significantly higher proportion of iron, magnesium, silicon, and carbon. These are the fundamental building blocks of terrestrial existence. They are the ingredients required to forge iron cores, silicate mantles, and rocky crusts. This chemical richness suggests that the primordial disk of dust and gas from which these stars were born was thick with the raw materials of geology. This wealth of heavy elements points to a profound possibility. The Alpha Centauri system was once a treasury of planetary potential. There were enough heavy atoms present to build dozens of worlds the size of Earth. In our own solar system, these elements were concentrated into the 4 rocky inner planets, but in a system with higher metallicity, the sheer volume of available material could have led to the formation of larger, more numerous, or more mineral-rich worlds. However, the very presence of these materials is a double-edged sword. While the chemistry provides the bricks and mortar for planets, the chaotic gravitational dance of the two suns provides the force that can either assemble them or tear them asunder. The spiraling embrace of Alpha and Beta creates a narrow corridor of stability. For a planet to survive for billions of years in this system, it must stay close to its parent sun, huddled within a small gravitational pocket where the influence of the second star is minimized. Outside of these narrow zones, the competing tugs of the two suns would likely eject any developing planet into the interstellar void, or send it spiraling into the fiery heart of one of the stars. Thus, the physical reality of Alpha Centauri is one of extreme contrast, a system rich with the chemical promise of life, yet governed by a gravitational master that demands absolute precision from any world that dares to exist within its light. The yellow and orange suns continue their 50-year pulse, a heartbeat of fire and gravity that has shaped the system for 5 billion years, leaving us to wonder what remains in the shadows of their brilliant heavy metal glow. The deceptive simplicity of our own solar system, where a single dominant sun dictates the orderly paths of its satellites, finds no purchase in the Alpha Centauri system. Here, the laws of motion are not a gentle guide but a chaotic master, a manifestation of the mathematical enigma known as the three-body problem. While the orbits of planets around a single star can be calculated with the precision of a clock for billions of years into the future, the introduction of a second or third massive body turns the heavens into a realm of unpredictable turbulence. This is the legacy of Henri Poincaré, the 19th century mathematician who first glimpsed the terrifying complexity of gravitational interaction. He realized that when 3 or more celestial bodies exert their influence upon one another, the resulting motion can become so sensitive to initial conditions that it defies long-term prediction. The clockwork universe of the ancients was replaced by a landscape of chaos, where even the slightest deviation can lead to a world being hurled into the frozen dark or consumed by stellar fire. In the Alpha Centauri system, this mathematical terror is a physical reality. A planet attempting to form around either Alpha Centauri Alpha or Beta is caught in a perpetual gravitational tug-of-war. As the two primary suns perform their 50-year orbital dance, the gravitational landscape is constantly shifting, warping the paths of any smaller objects in their vicinity. For a rocky world to survive, it must cling tightly to its parent star, dwelling within a narrow envelope of stability. If it ventures too far, the secondary sun begins to exert its own massive pull, stretching the planet's orbit into an elongated, unstable ellipse. This is a process of celestial grinding, where the competing tides of two suns work to dismantle the very foundations of planetary structure. The seasons on such a world would be a radical departure from the steady, tilt-driven cycles of Earth. On our home planet, the rhythm of the year is dictated by the 23-degree slant of our axis, a gentle variation in the angle of sunlight. On a world orbiting Alpha Centauri Alpha, the seasons are instead a product of the shifting proximity to a second orange sun. When Alpha Centauri Beta reaches its point of closest approach, it looms in the sky as a second, smaller furnace, its amber light washing out the stars and adding its thermal energy to the planetary atmosphere. This is a season of a double light and compounded heat, where the very air might boil under the combined radiation of two distinct suns. This period of intense warmth is not governed by the planet's own rotation, or tilt, but by the slow, 50-year pulse of the stars themselves. As the stars move toward their maximum separation, the secondary sun fades into a distant, piercing point of light, and the planet enters a long, cold twilight. The orbit of the planet itself may be wrenched and distorted during these transitions, leading to years that vary in length and climates that fluctuate with a violence unknown to our world. The atmosphere of such a planet is subjected to a constant erratic pumping of energy, creating weather patterns that are chaotic and extreme. There is no biological memory that could prepare life for a world where the suns themselves change their position in the sky over the course of a single lifetime, where the gravitational horizon is never fixed, and where the ground itself is subject to the tidal stresses of two massive masters. This gravitational instability acts as a filter, a violent struggle that prevents the formation of a peaceful, multi-planet system like our own. In the early stages of the system's life, when the protoplanetary disk was thick with dust and rock, the competing tugs of Alpha and Beta likely acted as a cosmic thresher. Smaller planetesimals were either flung out of the system entirely, becoming lonely wanderers in the interstellar void, or were sent on collision courses with one another. The result is a graveyard of failed worlds, a system where only the most resilient or the most tightly bound objects could endure. The very laws of physics that allow for the creation of planets in a single star system act as a destructive force here, ensuring that any world that remains is a survivor of a multi-billion-year war of attrition. The three-body problem is thus not merely a mathematical curiosity, but a fundamental constraint on the architecture of the universe. It defines the limits of where life can hope to find a stable foothold. In the Alpha Centauri system, the beauty of the double sunset is bought at the cost of orbital security. The celestial grinding continues, century after century, a rhythmic reminder that the stability we enjoy on Earth is a rare and precious gift. As the James Webb Space Telescope peers into this chaotic laboratory, it seeks the remnants of this struggle, the dust of shattered worlds and the heat of those few survivors that have managed to maintain their footing on the edge of the gravitational abyss. The system stands as a monument to the complexity of the dark, a place where the simple beauty of gravity reveals its most predatory and unpredictable nature. To witness the survivors of this gravitational thresher, the James Webb Space Telescope employs its most specialized and sensitive tool, the mid-infrared instrument, while the other cameras on the observatory operate in the near-infrared. Catching the ancient stretched light of the first galaxies, this instrument is tuned to the long, low-energy waves of heat itself. To function, it must be chilled to a temperature far below the rest of the telescope. While the sunshield keeps the main body of the craft at 40 degrees above absolute zero, the mid-infrared instrument requires an additional sophisticated cooling system, a cryo-cooler, to reach a staggering 7 degrees above absolute zero. This is a point where atomic motion nearly ceases. Inside this cryogenic heart, a 3-stage pulse tube and a Joule Thomson valve work in tandem to pump heat away, ensuring that the thermal noise of the telescope's own atoms is silenced. Only then can the sensors detect the incredibly faint infrared glow of distant matter without being drowned out by their own internal warmth. The primary challenge in observing the Alpha Centauri system is the overwhelming brilliance of the two main suns. They are millions of times brighter than any planet that might orbit them, creating a glare that would normally blind the telescope's detectors. To overcome this, the instrument utilizes a coronagraph. This is not a single piece of hardware, but a sophisticated optical system that acts as a physical barrier to the incoming starlight. It is a tribute to human ingenuity, a way to create an artificial eclipse millions of kilometers from home. Inside the instrument, a series of small opaque masks and specialized phase-shifting optics are positioned with the precision of a few micrometers. When the telescope is perfectly aligned, the concentrated light from Alpha Centauri Alpha or Beta falls directly onto one of these masks, which absorbs or deflects the majority of the stellar photons. This process is a masterclass in the manipulation of the wave nature of light. Light behaves as both a particle and a wave, and the coronagraph exploits this duality to perform a feat of optical magic. By using a 4-quadrant phase mask, the telescope takes the incoming waves of starlight and divides them. The mask is divided into 4 sections, each designed to shift the phase of the light by half a wavelength. As these waves recombine, they undergo destructive interference. The crest of one wave is met by the trough of another, causing the starlight to cancel itself out. The blinding glare of the sun is extinguished, leaving behind a dark, artificial stage. However, this cancellation only occurs for light coming from a specific central point. Any object located just a fraction of a degree away from the star, such as a planet or a disk of dust, is not cancelled. Its light passes through the optics untouched, emerging from the shadows as a tiny glowing ember against the blackness. What the telescope sees in this artificial darkness is not the reflected light we are accustomed to seeing from the planets in our own sky. Instead, it detects the thermal signature of the objects themselves. Every rock, every grain of dust, and every planetary atmosphere in the Alpha Centauri system radiates heat in the mid-infrared spectrum between 5 and 28 micrometers. In this range, a planet is not a dark sphere but a source of warmth. The telescope captures the photons emitted by the cooling crust of a world, or the heat trapped beneath a thick layer of clouds. This allows us to see the heat shadows of the system, the physical remnants of planetary formation that have been hidden for eons by the radiance of their parent suns. The glare of 2 suns is transformed into a dark stage where the secrets of the system are finally revealed. The precision required for this operation is staggering. The telescope must maintain its orientation with an accuracy that would be equivalent to hitting a coin with a laser pointer from a distance of several hundred kilometers. The reaction wheels and fine guidance sensors work in a silent, constant loop to counter the tiny pressures of sunlight and the movement of the telescope's own components. This is the pinnacle of human optical engineering, the culmination of centuries of progress from the brass tubes of the 19th century to the cryogenically cooled sensors of the modern era. We have learned to bend the very nature of light to our will, using the interference of waves to carve a window into the unknown. As the coronagraph blocks the light of Alpha Centauri, the space around the stars is no longer a blank void. The mid-infrared instrument turns the system from a blinding point of light into a detailed map of thermal energy. We see the faint glowing rings of dust that mark the paths of ancient collisions. We see the thermal signatures of debris belts that suggest a history of planetary upheaval. And in the gaps between these dusty shrouds, the telescope looks for the steady, unmoving glow of a planet, a world that has managed to maintain its footing in the chaotic dance of the 3-body problem. The golden eye has turned the glare into a dark theatre, and as the first frames of data are processed, the true, haunted nature of our nearest neighbour begins to emerge from the shadows. This is the moment where the dream of a second Earth meets the cold, hard reality of the infrared dark. The data streaming from the mid-infrared instrument does not reveal the vibrant blue-green oasis that centuries of human longing had hoped to find. Instead, the artificial darkness created by the coronagraph reveals a haunting landscape of devastation. The space surrounding Alpha Centauri Alpha and Beta is filled with a pervasive warm glow that indicates the presence of vast, dense belts of dust. These are not the clean, orderly rings of a young system, but the chaotic debris fields of a graveyard. This is exazodiacal dust on a scale far exceeding anything found in our own solar system. It is the pulverized remains of worlds that were never allowed to reach maturity, the silicate bone meal of planetesimals that were caught in the gravitational crossfire of the 2 suns and ground into nothingness over millions of years of high-speed collisions. In the infrared dark, these dust belts shine with a sickly persistent heat. They trace the orbits where planets should have been, marking the locations of ancient violent upheavals. The gravitational tides exerted by the two massive suns as they swing through their 50-year cycle act as a cosmic thresher, constantly stirring the planetary disk and preventing the calm accretion of matter. Any world that attempted to form in the regions between the two stars was subjected to relentless orbital perturbations. These worlds were stretched and squeezed by competing gravitational wells until their crusts cracked and their interiors were liquefied by tidal heating. Eventually, many were torn apart, their remains scattered into the vast glowing rings of debris that the James Webb Space Telescope now maps with chilling precision. Beyond the dust, the telescope detects the thermal signatures of the survivors, the few rocky bodies that have managed to maintain a precarious foothold in the system. But these are not worlds of water and life. They are scorched, airless rocks, basaltic plains that have been baked by the combined radiation of two suns for billions of years. The infrared data shows no evidence of the thick protective atmospheres that characterize worlds like Earth or Venus. Instead, these planets appear as naked skeletal husks. Their surfaces are exposed to the raw vacuum of space, their geological features sharpened by the lack of wind or rain, yet softened by the relentless bombardment of stellar particles. The absence of atmospheres on these worlds is the result of a process known as atmospheric stripping, a phenomenon that is amplified to a terrifying degree in a binary star system. Every star emits a stellar wind, a torrential stream of protons, electrons, and alpha particles that rushes outward at hundreds of kilometers per second. In the Alpha Centauri system, any planet orbiting within the theoretically habitable zone is caught in a permanent crossfire. As the planet moves through its orbit, it is sandblasted by the combined winds of both alpha and beta. Without a massive planetary-scale magnetic field to act as a shield, the upper layers of any atmosphere are ionized and carried away into the interstellar void. Over the course of millions of years, this relentless scouring removes every volatile compound. The water that might have filled oceans is broken down into hydrogen and oxygen by intense ultraviolet light. The light hydrogen escapes into space, while the oxygen is consumed by the rusting crust. Nitrogen and carbon dioxide are stripped away molecule by molecule, until nothing remains but a thin, tenuous veil of heavy gases, or more often, a total vacuum. The planets the telescope sees are the remnants of what might have been, the radiated cores of worlds that have lost their life-sustaining cloaks. They are monuments to the hostility of the binary environment, where the very light needed to warm a world is also the force that ensures its sterilization. The infrared images show these rocky husks as bright, hot spots against the blackness. Their dayside temperatures likely soar to hundreds of degrees Celsius, high enough to melt lead or turn sulfur into a gas, while their night sides are plunged into the absolute cold of the void. There is no atmosphere to redistribute the heat, no oceans to buffer the temperature, and no clouds to reflect the incoming glare. They are worlds of extreme contrast, where the landscape is defined by the harsh, unyielding geometry of radiation and shadow. The telescope reveals a system that is chemically rich and physically complex, yet biologically bankrupt. This discovery is a profound correction to the optimism of the previous century. The second Earth, that was once thought to be a certainty in our nearest neighbour, has been replaced by a collection of radiated ruins. The James Webb Space Telescope has pulled back the curtain on a reality that is far more haunting than we anticipated. We are looking at a system that possessed all the raw materials for life, the carbon, the iron, the silicate rock, yet lacked the one thing that our own solar system provides in abundance: stability. The golden eye of the telescope continues to gather its data, mapping the dust and the debris, providing a detailed census of a graveyard that spans trillions of kilometers. These are the silent monuments to the infinite complexity of the dark, a reminder that the path to a living world is a narrow and perilous one, easily closed by the chaotic dance of the stars. Far beyond the scorched remains and the grinding gravitational tides of the central pair, the system extends its reach into a much deeper, colder silence. To find the final member of this trinity, one must travel outward from the brilliant yellow and orange suns, crossing a distance of 13,000 astronomical units. This is a gap of 1/5 of a light year, a distance so vast that the light from Alpha and Beta takes months to reach this lonely outpost. Here, lurking in the shadows of the interstellar medium, is Proxima Centauri. It is the closest star to our own Sun, yet it is a celestial paradox, a neighbour that is fundamentally invisible to the unaided human eye. While its cousins are giants of light, Proxima is a dim crimson ember, a star that smoulders with a sullen and deep red intensity. Proxima is a red dwarf, a member of the most common and longest-lived class of stars in the Milky Way galaxy. In terms of physical scale, it is a study in extreme compression. Its diameter is only about 1.5 times that of the planet Jupiter, making it a tiny speck compared to the vast volume of our Sun. However, this small size belies a formidable mass. Proxima contains more than 120 times the mass of Jupiter, packed into a sphere of such incredible density that the pressures at its core are sufficient to ignite the slow, steady fuse of nuclear fusion. It is a star at the very lower limit of stellar existence. If it were even slightly less massive, it would have failed to ignite altogether, doomed to spend eternity as a brown dwarf, a planetary ghost that never truly found its fire. The nature of this fire is what defines Proxima's place in the cosmic hierarchy. Unlike our Sun, which possesses a radiative zone where energy struggles to move through dense layers of gas, Proxima is fully convective. It churns like a boiling cauldron from its core to its surface. This constant mixing means that the star is never stratified. It continuously cycles fresh hydrogen from its outer layers down into the nuclear furnace at its heart. Because of this efficient process, Proxima burns its fuel with a parsimony that is almost incomprehensible. While our Sun is a middle-aged star that will exhaust its hydrogen in another 5 billion years, Proxima is barely at the beginning of its journey. It is destined to burn for 4 trillion years, a span of time that makes the current age of the universe seem like a mere heartbeat. This longevity makes Proxima Centauri a witness to the deep future of the cosmos. It is the lonely cousin of the system, a star that will remain long after Alpha and Beta have expanded into red giants and faded into white dwarfs. Yet, despite its long life, it is a star of profound dimness. It radiates less than 0.1% of the luminosity of our Sun. Most of its energy is emitted in the infrared spectrum, invisible to human eyes but brilliantly clear to the sensors of the James Webb Space Telescope. To stand on a hypothetical planet orbiting Proxima would be to live in a world of permanent twilight, where the Sun is a bloated, deep red disk that provides warmth without the blinding brilliance we associate with daylight. Proxima represents the silent majority of the galaxy. 3 out of every 4 stars in the Milky Way are red dwarfs like this one. To understand Proxima is to understand the primary habitat of the universe. For decades, astronomers looked at this dim ember as a secondary thought, a small companion barely held by the gravitational leash of the 2 larger suns. Indeed, its orbit around the central pair is so wide and so slow that it takes over 500,000 years to complete a single revolution. It drifts on the very edge of the system's gravitational well, a star that is only just barely bound to its family, a wanderer that spends most of its time in the dark. The James Webb Space Telescope turns its gaze toward this crimson point of light not for its brilliance, but for its secrets. Because Proxima is so small and so dim, any planet orbiting it becomes much easier to detect. The star does not overwhelm the thermal signatures of its satellites with the same ferocity as its larger cousins. This has led to the discovery of Proxima Centauri b, a world that exists within the star's habitable zone, the narrow region where temperatures might allow for the existence of liquid water. But the proximity required for this warmth is a dangerous gamble. Because Proxima is so dim, its habitable zone is 20 times closer than the Earth is to our Sun. This brings the planet into a realm where the star's physical presence is not a gentle warmth, but a looming, unpredictable threat. Proxima may be a slow-burning ember that will outlast the stars themselves, but it is far from a peaceful neighbour. It is a star of hidden violence, a smouldering coal that can, without warning, erupt into a furnace of lethal energy. As we move closer to this crimson sun, the promise of a long-lived world begins to clash with the reality of a star that refuses to remain quiet in the dark. The deceptive stillness of this crimson sun is a mask for a magnetic ferocity that defines the existence of everything in its orbit. Because Proxima Centauri is fully convective, its entire interior is a churning cauldron of ionized gas, a process that generates magnetic fields of staggering complexity and strength. These fields do not lie flat across the surface. They are twisted, coiled, and knotted by the star's rotation until they reach a point of catastrophic tension. This is the origin of the Proxima tantrum, a phenomenon that transforms a dim ember into a lethal furnace in a matter of seconds. When these tangled magnetic lines finally snap and reconnect, they release a torrent of energy known as a superflare. The scale of such an event defies the common understanding of stellar behavior. In a single eruptive burst, Proxima Centauri can release the energy equivalent of 1 billion nuclear bombs detonating simultaneously. The star's luminosity, normally a fraction of our sun's, can increase by a factor of 1,000 in less than a minute. This is not the steady, life-giving warmth of a yellow dwarf, but a violent, unpredictable pulse of radiation. For a world like Proxima Centauri b, which orbits a mere 7.5 million kilometers from its sun, 20 times closer than the Earth is to our own star, there is no escape from this fury. The planet exists as a flickering candle in a hurricane, where the very light required for its warmth is also the force that threatens to extinguish its biological potential. As the superflare erupts, the first wave of destruction arrives at the speed of light. A deluge of high-energy X-rays and extreme ultraviolet radiation slams into the planet's upper atmosphere. On Earth, our thick atmosphere and robust magnetic field shield us from the sun's occasional flares, but Proxima Centauri b is subjected to a bombardment hundreds of times more intense. The radiation penetrates deep into the gaseous envelope, stripping electrons from atoms in a process called ionization. This turns the once stable air into a chaotic plasma, which is then easily carried away by the following shockwave of the stellar wind. This is not a gradual erosion, it is a violent scouring, a rhythmic peeling away of the world's protective layers. Following the initial flash of light, a massive cloud of charged particles, a coronal mass ejection, barrels across the narrow gap between the star and the planet. This wall of plasma, moving at millions of kilometers per hour, strikes the planet with the force of a physical blow. If the planet possesses a magnetic field, it is compressed and distorted, its lines of force glowing with the intensity of 1,000 auroras. But even the strongest magnetic shield can be overwhelmed by the sheer frequency of these tantrums. Proxima Centauri can erupt with multiple superflares in a single day, ensuring that the planet never has time to recover. The atmosphere is not just stripped, it is prevented from ever regenerating. On the surface of the world, the consequences are absolute. Without a thick atmosphere to filter the incoming radiation, the landscape is bathed in a lethal glow. The ultraviolet light is strong enough to shatter the molecular bonds of deoxyribonucleic acid and other complex organic compounds. Any liquid water that might have pooled on the surface during the star's quieter periods is vaporized and broken down into its constituent atoms, with the light hydrogen escaping into the void and the oxygen reacting with the parched iron-rich soil. The world is turned into a sterilized desert of basalt and rust, a place where the chemistry of life is interrupted before it can even begin. This is the paradox of the red dwarf habitable zone. To be warm enough for liquid water, a planet must be so close to its sun that it is perpetually within the reach of these magnetic tantrums. The habitable label becomes a cruel irony. It is a region of space where the energy for life is present, but the stability required for life is absent. The planet Proxima Centauri b, for all its similarity in mass and size to the Earth, is a victim of its environment. It is a world of permanent day and permanent night, tidally locked to its master, with the day side receiving a constant pounding from a star that cannot control its own temper. The James Webb Space Telescope, observing the system in the mid-infrared, sees the thermal echoes of this violence. It detects the heat of a world that is being slowly dismantled by its own sun. The data reveals a lack of the chemical signatures associated with life, No methane, no ozone, no water vapor. Instead, it finds the signature of a world that has been scoured to the bone. This realization forces a shift in our understanding of the most common stars in the universe. If the billions of red dwarfs in our galaxy are all prone to such tantrums, then the vast majority of habitable planets may in fact be radiated graveyards. The flickering candle of Proxima Centauri b serves as a warning. In the search for a second home, the quality of the light is just as important as the quantity. The universe may be filled with suns, but very few of them possess the steady, nurturing hand required to foster the slow, delicate bloom of biology. The realization that our nearest neighbours are hostile, radiated graveyards does not dampen the human impulse to explore. It merely changes the nature of the tools we must use. The limitations of even the most powerful telescopes eventually reach a hard physical wall, a boundary where the resolution of a distant lens can no longer suffice to reveal the fine details of a planetary surface. To truly know the Alpha Centauri system, to touch the scorched basalt of its worlds, and measure the true intensity of its flares, humanity prepares to send a physical extension of itself across the void. This vision is embodied in Project Breakthrough Starshot, an engineering feat that seeks to bypass the limitations of chemical rockets by harnessing the momentum of light itself. The centerpiece of this mission is the Starchip, a wafer of refined silicon no larger than a postage stamp and weighing less than 1 gram. Within this tiny sliver of matter, the functions of a full-scale spacecraft are compressed. Microscopic cameras, navigation sensors, a sub-gram power source, and a laser transmitter capable of sending data back across the 4-light-year gulf. Attached to this silicon heart is a light sail, a gossamer sheet of advanced material only a few hundred atoms thick. It is a square of shimmering reflective film that spans several meters yet possesses almost no mass. The materials for such a sail must be exotic, capable of reflecting 99.999% of the light that strikes them to avoid being instantly vaporized by the energy they are designed to harness. The propulsion for this craft does not come from burning fuel, but from a gargantuan array of ground-based lasers on Earth. This light beamer, a square kilometer of phased array lasers, focuses 100 gigawatts of power into a single, coherent pillar of light that strikes the sail. The pressure exerted by these trillions of photons is a physical force, a relentless push that provides a brutal, sustained acceleration. Within minutes of the laser ignition, the Starship is propelled to 20% the speed of light, 60,000 kilometers per second. The acceleration is a staggering 60,000 times the force of gravity, a speed that would allow a craft to reach the moon in less than 7 seconds. This velocity turns the interstellar crossing from a multi-generational odyssey into a 20-year sprint. Once the laser array falls silent, the Starship enters a phase of profound, lonely isolation. It is now a silicon ghost, hurtling through the interstellar medium at a speed that turns the sparse vacuum into a lethal obstacle course. At 20% the speed of light, the nature of space itself changes. The dilute plasma and stray atoms of the void become a high-energy bombardment, and the blue-shifted light of the stars ahead begins to warp the probe's perception of the universe. The primary hazard of this 20-year journey is the sheer kinetic energy of the vacuum. The interstellar medium is not truly empty. It is populated by microscopic grains of dust, the remnants of ancient supernova, and the debris of planetary formation. At 60,000 kilometers per second, a collision with a single grain of dust, no larger than a speck of soot, is a catastrophic event. The kinetic energy released by such a strike is equivalent to the detonation of a hand grenade. Because the probe is moving so fast, there is no time for sensors to detect the grain, or for thrusters to move the sail. The Starship must be built with a leading edge of sacrificial armor, or the mission must rely on the statistical hope that the void is empty enough to allow passage. The project envisions launching thousands of these tiny sails, a swarm of silicon explorers where the loss of 99% of the fleet is an acceptable cost for the success of the few that remain intact. For 2 decades, the probe streaks through the dark in absolute silence. There is no sound of an engine, no vibration of a hull, only the unyielding momentum of its flight. It carries with it the sum of human curiosity on a sliver of silicon, a testament to a species that refuses to be bound by the gravity of its birth. The communication with Earth is a slow, difficult process. A signal sent from the probe takes over 4 years to reach the waiting ears of the Deep Space Network. As the starship approaches the Alpha Centauri system, the light from the 3 suns begins to grow, shifting from distant sparks to dominant furnaces. The probe must use its tiny onboard thrusters to perform a flyby of the target planets in a matter of hours, as it possesses no way to slow down. It is a high-speed gamble against the silence of the infinite dark. The journey of the starship is a bridge between the era of observation and the era of presence. It represents the moment humanity stops merely looking at the neighbours and starts reaching out to touch them. In the lonely transit between the stars, the probe is the only thing that exists in the vast gap, a tiny spark of intelligence in a desert of light years. It is a creation of light and silicon, designed to survive the Proxima tantrum and the gravitational grinding of the central suns, all to capture a few moments of data that will change our understanding of the cosmos forever. The crossing of the void is no longer a dream of the distant future, but a calculated high-speed sprint toward the secrets of the 3 suns. 5 billion years from now, the era of yellow suns begins to draw to a close. The steady fusion of hydrogen that has powered our sun since the dawn of the solar system finally exhausts its supply, and the delicate equilibrium between the inward crush of gravity and the outward pressure of nuclear fire collapses. The sun's core, now a dense knot of helium, contracts with such ferocity that the surrounding layers of hydrogen ignite in a final desperate shell. The star bloats outward, its atmosphere expanding until it becomes a red giant, a gargantuan glowing sphere that swallows the inner planets and turns the Earth into a scorched, airless cinder. This same destiny awaits Alpha Centauri Alpha and Beta. Within a few 100 million years of their expansion, they too will shed their outer envelopes, creating brilliant planetary nebulae that drift away into the void, leaving behind only their white dwarf cores, stellar corpses the size of Earth but with the mass of a sun, cooling slowly into the eternal dark. But while the primary suns of the nearest system fade into white dwarf ghosts, Proxima Centauri remains. This small crimson star is the ultimate survivor of the stellar age. Because of its low mass and its fully convective interior, it burns its fuel with a parsimony that is almost incomprehensible. It does not possess the stratified layers of its larger cousins. Instead, it churns like a boiling cauldron, continuously cycling fresh hydrogen from its surface down into the nuclear furnace at its heart. This efficiency allows Proxima to remain on the main sequence for 4 trillion years. To understand the scale of this longevity, one must consider that the universe is currently only 13.8 billion years old. Proxima Centauri will continue to smoulder long after every other bright star in the Milky Way has guttered and died. It will witness the birth and death of 1,000 generations of stars like our Sun, a solitary ember in a darkening galaxy. As the hundreds of billions of years turn into trillions, the universe enters the era of the long twilight. The vast clouds of gas and dust that once birthed new stars are exhausted, and the galaxy becomes a graveyard of stellar remnants. The brilliant spiral arms of the Milky Way dissolve as the bright blue giants and steady yellow dwarfs wink out one by one. In this distant epoch, the only remaining sources of light and heat are the red dwarfs. Proxima Centauri becomes a vital outpost, one of the last witnesses to the end of the stellar age. Any consciousness that survives into this era would find the universe a cold and lonely place, where the stars are no longer a tapestry of light, but a few scattered dim red points separated by vast expanding gulfs of absolute blackness. The expansion of space driven by dark energy will have pushed all other galaxies beyond the cosmic horizon, leaving the Milky Way, now merged with Andromeda, as a solitary island in an unreachable void. The nature of the Alpha Centauri system will have shifted from a chaotic laboratory of fire into a quiet, frozen monument. The 2 white dwarfs that were once Alpha and Beta will have cooled significantly, their brilliant white light fading into a dull orange-red glow, and eventually into a deep infrared heat that is invisible to the eye. They will continue their 50-year orbital dance, but they will do so in a system stripped of its dust belts and its scorched planets. The gravitational tides that once ground worlds into powder will now only act upon the two dead cores themselves. Far in the distance, Proxima Centauri will still be burning, a tiny red spark that provides the only significant energy in the entire local neighbourhood. It will be the last sun of the system, a star that refused to die when the rest of the universe began its long descent into the dark. Eventually, even the endurance of Proxima Centauri reaches its limit. After 4 trillion years, the last of its hydrogen will be consumed. It will not expand into a red giant, for it lacks the mass for such a transition. Instead, it will slowly turn into a blue dwarf as its surface temperature rises, and finally it will collapse into a white dwarf composed mostly of helium. The Alpha Centauri system will then consist of 3 cold, dark husks, 3 dead suns locked in a permanent silent orbit. These white dwarfs will continue to cool for quintillions of years, eventually becoming black dwarfs, theoretical objects that have cooled so much they no longer emit any heat or light. They will be dark, solid spheres of degenerate matter, drifting through a universe that has grown cold and empty. The stellar age of the universe will draw to its final close, and the cosmos will enter the era of the black holes, where the only energy remaining is the slow, hawking radiation of the dark giants. The long twilight ends in absolute silence, a testament to the fact that even the most resilient stars are but fleeting sparks in the infinite duration of the void. The Alpha Centauri system, which once represented the nearest hope for a second home for humanity, will end as a collection of dark monuments, silent witnesses to a time when the universe was filled with light and the possibility of life. The journey from the golden mirrors of the James Webb Space Telescope to the final fade of Proxima Centauri is the story of the universe itself, a brief, brilliant flash of complexity and fire before the inevitable return to the equilibrium of the dark. The stream of data from the second Lagrange point is more than a collection of infrared measurements. It is a profound revision of the human story. For centuries, the Alpha Centauri system served as a blank canvas for our aspirations, a place where we projected the hope of a second chance and the dream of a mirror world. The James Webb Space Telescope has shattered that mirror, replacing the comforting myth of a twin Earth with the stark, unyielding reality of a stellar laboratory. We now see that the proximity of these stars is not an invitation, but a warning of the precariousness of life. The golden eye has revealed that the conditions we take for granted, a stable orbit, a protective magnetic shield, and a steady, predictable sun, are not the universal standard, but a rare and fragile confluence of circumstances. In the light of these findings, our own world, the pale blue dot drifting in the relative quiet of the solar system, takes on a new and more precious significance. It is a solitary sanctuary, a protected harbour in a galactic neighbourhood defined by gravitational grinding and stellar tantrums. While the planets of Alpha Centauri are scoured by the combined winds of 2 suns or pulverised by the chaos of the 3-body problem, the Earth resides in a pocket of profound stability. We are the beneficiaries of a cosmic lottery, living on a world where the laws of physics have conspired to allow for the slow, multi-billion-year evolution of complexity. The silence of the Alpha Centauri graveyard emphasizes the sheer improbability of our existence. We occupy a narrow window of peace in a universe that is fundamentally indifferent to the biology it occasionally produces. There is a haunting beauty to be found in this terror. The universe is not a garden designed for our comfort, but a vast and often hostile machine of fire and vacuum. Yet, the fact that a collection of biological organisms, evolved from the mud of a single planet, can construct a machine of gold and beryllium to peer across the 40 trillion kilometre void is a triumph of the highest order. We have used our understanding of the laws of nature to transcend our own physical limitations. We have learned to read the chemistry of distant suns and to map the heat shadows of failed worlds, turning the terrifying vastness into a landscape of knowledge. The scarier truth is not that the universe is empty, but that it is filled with worlds that are almost like ours yet remain forever out of reach, silent monuments to the infinite complexity of the dark. This realization does not diminish the human spirit, it defines it. We are a species that finds meaning in the act of looking, even when the view is daunting. The James Webb Space Telescope is the physical manifestation of this impulse, a bridge between the finite reach of our bodies and the infinite scale of the cosmos. It shows us that while we may be physically small, our capacity for understanding is as vast as the space between the stars. We have transformed the Alpha Centauri system from a mythological mystery into a physical reality, and in doing so, we have gained a deeper appreciation for the miracle of our own survival. The beauty of the cosmos lies not in its hospitality, but in the fact that it is intelligible to us. Our curiosity is the flame that illuminates the abyss. Even as we recognize the hostility of the stars, we do not turn away. We continue to build, to calculate, and to reach out. The James Webb Space Telescope remains at its post, 1.5 million kilometers from the warmth of home, a small and fragile creation of human hands and minds. It continues its silent vigil, its golden mirrors catching the light of a universe that does not know we exist. In the absolute quiet of the second Lagrange point, the machine stares into the dark, a testament to a species that dares to look into the mouth of the furnace and find the beauty in the fire. We are a part of the universe seeking to understand itself, a brief and brilliant spark of awareness in a cosmos of giants and shadows. As the telescope pivots to its next target, it carries with it the weight of our questions and the persistence of our wonder. It stands as a lonely sentinel at the edge of the infinite, a reminder that we are the only ones who can give the universe a voice. The data from Alpha Centauri has taught us that we are more alone than we thought, but it has also shown us that we are more capable than we ever dreamed. The golden mirrors reflect not just the light of distant suns, but the courage of a species that refuses to be intimidated by the dark. In the end, the story of Alpha Centauri is the story of ourselves, a journey of discovery that leads us back to the realization that our home is a rare and precious jewel, and that our greatest strength is the courage to look into the void and see it for what it truly is. The machine continues its work, unblinking and precise, as the stars continue their ancient, indifferent dance across the deep.